Start the YouTube as well. All right. So I welcome you all to this special talk organized by our the SCOPE committee, which stands for, yeah. So, okay, continue with our Science Communication Public Outreach and Education Committee, which stands for SCOPE IAA, is inviting you all to this special evening talk. For us, it's evening, and for Andrew, it's a morning. And a special talk on the occasion of the World Space Week. And to give just a brief outline of what it means, World Space Week is annually observed between October 4th to 10th all over the world. And this is officially defined as an international celebration of science and technology and their contribution to the betterment of the human condition. And this is positioned during this period. That's the choice of dates, is coming basically from two important dates in space history. There's the launch of the first human-made Earth satellite Sputnik 1 on October 4th, in 1957, and the signing of the Outer Space Treaty on October 10th, 1967. And the theme changes every year, and which is decided by the the board of directors of the World Space Week Association. And this year it happens to be Women in Space. And I think you would have heard about this in other talks as well, but then I thought it's a good thing to put things in context. And we have a special talk by Andrew, and it's related to asteroids. And definitely he'll be speaking to us, and looking forward to listen to him regarding the project which he's involved in. And that's all from my side. And I hope you all enjoy the talk and learn more about asteroids and the project Andrew is doing. Yeah, back to you, Chrisphin. It's fine in Zoom.
All right. Thank you very much for inviting me, and it's great to be here giving this talk for World Space Week. It's I guess a bit of a shame. I've never been to India, so it's too bad I have to give this sitting at my dining room table instead of there in person. But thank you so much for having me. So as noted, let's see. Also, I'll share the screen, and so I'll be talking about planetary defense and the DART mission, as noted. So so here we go. This just shows some of the major partners. Of course, as with anything in space, nothing happens. Nobody does anything alone, and so we have a lot of partners on DART, including, of course, NASA, who's paying for all this, but also a lot of universities and aerospace companies. These are just the U.S. companies. So, why do we care about planetary defense, and what is planetary defense? This map of the world has as an overlay all of the impacts that have been detected by satellites looking down. When they look down, they see a flash. It is basically always due to something hitting the Earth, although these could be very small. So the impact energy is kind of given there on the right in this color bar, and also by the size of the circle. Many of these are very small, maybe only the size of the laptop that that many of us are using to watch or give this talk. But some of them can be pretty big. The largest impact that we have detected, or that is within certainly at least living memory, if not I guess within the last century, is this large circle kind of over Siberia. This was over the town of Chelyabinsk in Siberia. It happened in 2013. And this was, perhaps you've seen pictures. There are, those of you watching on YouTube can easily find after the talk, I guess, videos of this impact over Siberia. There was a big flash, there was a fireball, and then a minute or so later, there was a big sonic boom, which blew out windows all throughout the town and ended up injuring about 1,000 people. So this was caused by the impact of an asteroid that was only about 20 meters across, but it still created a brought impact energy equivalent to 500 kilotons of TNT. There have been some larger ones. The largest within history, I believe, was something that hit also in Siberia. I don't know if there's something about Siberia, near Tunguska. This was before radio, before television, in 1908. It was in a pretty remote part of Siberia, so it took a very long time to figure out what was going on. And in fact, it wasn't truly concluded that this was due to an asteroid impact until within the last few decades, but that's clearly what it was. The impact of an object may be somewhere between 60 and 190 meters, and that impact was 5 megatons of TNT, so very large. And even though they didn't have sophisticated scientific equipment, they didn't have satellites in 1908. They didn't have any of those things. The crude weather instruments that they had at the time were still able to detect it. And then perhaps the most famous impact of all, that ended the Cretaceous period, and is responsible for killing most of the dinosaurs, most of the non-avian dinosaurs, occurred 65 million years ago, and that was something much larger, maybe the size of 10 to 15 kilometers. Whoops. So how often do these things happen? As you might imagine, smaller impacts, as you saw from that map, can happen pretty often. About every year we get hit by something a few meters across. Those don't reach the ground often. They're too small. They are affected by the atmosphere. They burn up in the atmosphere. You'll see a flash, but there could be little pieces that make it to the ground as meteorites that then get studied. something the size of Chelyabinsk, which is about 25 meters. We think they happen every century or so. As you get larger and larger, they happen less and less often. So something like the impact that killed the dinosaurs, we're thinking is something that happens only every 100 to 200 million years. But obviously, we'd want to know about all of these impacts, anything that could cause widespread damage on Earth, and maybe is happening more often than every 100 to 200 million years, is something we in particular might want to be concerned about. And that falls in this kilometer size range to maybe 150 to 160 meters. At the size of a kilometer, we think an impactor would have enough effect that it might, basically be a serious problem for everyone on Earth. It might cause the, global devastation. It might cause crops to fail all over the world. It might change the climate immediately in a way that is very dramatic. We think there are about 900 objects of that size that have orbits that are close-ish to Earth. None of them will hit the Earth. We are feeling pretty good about that. We feel like we've got a good handle on the number of 1 kilometer objects out there. And I will also stress now and later that we know of no objects that are going to hit the Earth. We don't feel like there's any imminent danger or anything that we know that's going to hit the Earth for at least a few centuries. As you get to smaller sizes, those impacts happen more often, and we know of fewer of those objects. Something about the size of 160 meters could still leave a pretty big crater, and it could be a bad problem if something that big hit a city or near a city. We expect there to be something like 20,000 of those objects out there. We've found less than half, so we're less confident about what our future is for those. The odds are good. The odds are in our favor that if we do find something, or as we find more of these objects, they're not likely to hit the Earth. But of course, we need to go out and look. There is physical evidence of asteroid impacts in the past that show what some of the consequences can be. There's a crater in Arizona in the United States called Barringer Crater, also called Meteor Crater. Here's a satellite photo. And overlaid on that in different colors are circles that show the different effects as you get closer and closer to the crater. Within 10 kilometers of the crater, you would of that crater, if you had been there would have been a fireball. Large animals would have been killed or wounded within 24 kilometers. And hurricane force winds, or I guess cyclone or typhoon force winds, would go even further out. If you overlaid this onto a city, like where I live just off the edge of this map. Oh no, I'm just at the edge of this map. That's where I'm calling you from here, and that's where I am. And you overlay those colors, it could be very bad. So again, we want to understand what's out there, and make sure that we at least know what's coming, or hopefully that nothing will be coming. So planetary defense is the field of trying to deal with what's out there. This is a graphic made by the NASA Planetary Defense Coordination Office, and it basically shows the different pieces of the problem. Up in the upper right, there's the question of finding what's out there, searching with telescopes on the ground or in space to find what's out there. Here in the lower right, you have characterization. This is once you've found an asteroid as a point of light, trying to figure out, is it made of rock? Is it made of metal? How big is it? How fast is it spinning? And then being able to use that information to make educated guesses about what else is out there and what its nature is. The other thing that involves scientists, since some of these, like plan and coordinate and assess, involve managers and engineers, the other one that is of interest for for us today, or tonight for you, is mitigation. If you find something, what are you going to do about it? And this is where DART falls. DART, the mission I'm going to be talking about, is under this mitigation property category, and again is managed by the NASA Planetary Defense Coordination Office, which is pretty new. So testing a mitigation mission is something that has been a high priority for the community for some time. And we, on the right here, we have kind of a graphic that shows the 3 or 4, I guess, 4 ways we think we would deal with an asteroid impact if something were coming. The largest, well, I'll go in the other direction. The smallest objects down here, this plot shows size on the y-axis and the amount of warning time we have on the x-axis. If something is small enough, it is going to be most effective to just take the hit. If we knew that the Chelyabinsk impactor was coming ahead of time, and we know, okay, that's going to be the injuries caused in the Chelyabinsk impact were because people rushed to the window to see what happened, and then the windows broke. So we would say, look, there's going to be a flash over your city. You can go out and look at the flash, but make sure you're not anywhere near a window in the next 5 minutes after the flash, because the windows are going to break. And it's cheaper to just fix everyone's windows than it is to go and send a mission. At the very largest sizes, or if we don't have a lot of warning, the biggest tool that we have as humankind is a nuclear device. So this would not happen exactly like in the movies. We would not try to blow up an object and disperse it. We'd probably explode the nuclear device off to the side and let it melt and vaporize some of the asteroid to move it. A lot of people are very uncomfortable with this option for all sorts of good reasons. By international law, you cannot test nuclear packages, nuclear devices in space. So there's been a lot of interest in developing other things that could be used. The gravity tractor is this technique kind of here in the corner. Basically, this has been developed, and the idea is that because all masses attract to one another, you would send a large, very massive spacecraft. You would park it next to the asteroid you want to move, and then you would use the gravity of the spacecraft and the attraction that the asteroid has to that to slowly move the asteroid out of the way. And then this fourth one is called a kinetic impactor. And that's what DART is. Basically, it is taking your spacecraft and ramming it into the asteroid, and then using the momentum that you bring from the spacecraft to add to the momentum of the asteroid and change the asteroid's orbit. So it's a very, very simple concept, but it is something we think we could do now, but we would like to test it and make sure there aren't any wrinkles that we weren't expecting. Every time we send an asteroid mission, we find something that we weren't expecting before we went. So just a very quick description of the DART mission here. We, as noted, are scheduled to launch very soon, only a little over a month from the Vandenberg Space Force Base. We're going to launch on a SpaceX rocket. We then arrive at our target, which is an asteroid moon named Dimorphos, in a little under a year. So this is going to all happen very, very quickly. Dimorphos is a moon, like I said. It's orbiting another asteroid, the asteroid Didymos. We're carrying a CubeSat, which is built by the Italian Space Agency. And then once the impact occurs, the impact between DART and the asteroid, we're going to be making measurements from the Earth. So I'll talk about all of this much more over the course of the rest of the talk. So this is just a quick animation that was made that shows kind of the last moments of the mission. And this is the plan to fly in and take our spacecraft and hit the asteroid moon. So this it doesn't look like it's gonna be very big potentially, but it is big enough. This shows the scale of the objects that we're talking about here. DART is here on the left. It's 19 meters across with the solar panels extended. If you don't count the solar panels, it's about the size of a vending machine, at least a US vending machine. I'm assuming Indian vending machines are about the same size. I guess I don't know. The asteroid we're going to hit, the moon, is about the size of one of the Great Pyramids of Giza. So about 160 meters. And then the object it's orbiting, Didymos, is 4 or 5 times larger. And it is about the same diameter as the Burj Khalifa, which is the tallest skyscraper on Earth. This shows the path DART will take. Didymos's orbit comes close to Earth, but does not intersect it. Didymos itself is not a dangerous asteroid. It is not a hazard to Earth. So DART launches. It stays in an orbit very close to Earth, kind of goes around the sun once before impacting Dimorphos at, like I said, in just about a year. So that's, at the top scale, what DART is going to do, but we of course have a lot of very specific things, more than we've said. In order to be considered a success, any NASA mission, and I suppose any mission by any space agency, including ISRO, has to define what it's going to do, and then do those things. Otherwise, the mission's not considered a success. So there are 4 top level requirements that DART has to achieve in order to be to do what we intend. First is to actually hit Dimorphos, and it's going to do that again, in under a year. We have to change the orbit period of the moon around the main body by at least 73 seconds. The orbit period right now is about 12 hours, so it's a small fraction, but one that we can measure from Earth, one that we can detect. The third requirement is that we have to make a good measurement of what we have done. So we have to measure the change that we make in the period to within 7.3 seconds. And then for this fourth one, this one is a little more complicated, but I have a couple of slides on it coming up, which is basically to measure what's called the momentum enhancement factor, or beta. Like I said, we take the momentum from the spacecraft and we add it to the momentum of the asteroid. And of course, if you've taken physics, and I'm sure most or all of you have, momentum is conserved in a closed system. But we don't think this is going to be a closed system. We're going to make debris. The debris is going to leave. It's going to carry momentum with it. So we need to understand how much of the momentum we carry in with the spacecraft gets translated into a change in momentum of the main body. This graphically shows again what we're going to do. We're going to impact Dimorphos. We're going to come as close to head on as we can. And that is going to take energy out of Dimorphos's orbit and drop it into a slightly smaller orbit around Didymos. I think the change in the semi-major axis, the change in distance from Didymos, is only going to be a few meters out of a kilometer. But again, that will be enough for us to measure. The way we're going to measure it is with our telescopes on Earth and in space, using a technique that we call light curve measurement. While they are two bodies in space, from the ground and from basically all of our telescopes, including Hubble and the JWST, if assuming that gets its measurements, this will only appear as one point of light. They're too close together, too small to appear as two different objects. They'll appear as one point of light from our telescopes. But what we can do is measure the brightness of that point of light, and as Dimorphos goes around Didymos, it will block some of the light as it passes in front and casts a shadow. And then it will also get a little bit fainter as Dimorphos is blocked by Didymos in turn, and these little eclipses happen. By measuring the frequency of these mutual events, as we call it, when the moon moves in front and in back, that's what tells us the orbit period of Dimorphos. We've been making these measurements since 2015 or so, so we have a very good idea of the orbit period now before we go and mess it up. And then after the impact, we will then go and make these measurements again, which will let us know what we've done. So as I said, there's this beta factor. We do not think we're going to have a, well, there's this beta factor. In a situation where it is a closed system, if somehow we don't make any debris, we don't kick anything off the surface, then beta is going to equal 1. But again, we expect to make some ejecta. And we expect that ejecta will escape the system with carrying momentum with it. We don't know how much, and we don't know how fast. So it's possible that there will be a factor of 2 additional change in Dimorphos's momentum, because the momentum and the ejecta is moving opposite the direction that DART came in, so that gives it an extra push. Some of the models suggest that beta will actually be pretty small. Maybe it'll be 1.2 or 1.3. If Dimorphos is a more solid rock, or if we hit something that's a big boulder, then we could get some of these larger betas of 2 or 4 or even more. And the way we understand this is by doing impact modeling in the laboratories. This is an animation of one of those impact models done by people on the DART team, showing an impact coming into a rubble pile, as we call it, a big bunch of different sized rocks. And then you can keep track of the material coming off of the surface and its momentum, and make these estimates of what beta will be. And you can do this many times with all sorts of different materials and come out with your estimates. These models are not meant to show the DART impact per se, but just different sort of small scale impacts. And these have beta values that vary, that can be pulled out of the models. So let's talk about the spacecraft. You saw the scale before, like I said, about the size of a vending machine, and there will be some pictures later. DART is a pretty simple spacecraft, unlike some of the spacecraft that go to Saturn or Mars or a comet or Venus or Mercury. There's only one instrument. It's a camera called Draco. And it's based on the camera that has gone to Pluto. Actually, it's on the New Horizons spacecraft. There are solar panels that, when extended, are again, I guess 10 meters, almost 10 meters, 8 meters maybe, in length, but they start out rolled up. This is one of the new technologies we're gonna be testing. And then we have a ion engine. Here, these are both shown as they are now with their covers on, but those covers will come off to allow them to operate. This is the set of new technologies that are being tested and flown. The smart nav is the algorithms that are going to allow DART to hit Dimorphos. We don't have someone sitting there with a joystick trying to steer it in. The keys to the car, so to speak, are handed off to smart nav an hour or so out. And it's going to take the images from the Draco imager, determine where Dimorphos is, and then keep pointing at it. The rollout solar arrays, as I mentioned, are a new technology. Assuming they work, and we have no reason to think they won't, then they will allow big solar panels to be fit into much smaller areas and much smaller rockets for launch. The LiCiCube CubeSat is, as I mentioned at the start, built by the Italians. I have a separate slide on that coming up. And then there are some of these other technologies that are, again, of maybe less flashy, but are of definite interest to making space missions more effective and lower cost. So here's LiCiCube. It's a 6U CubeSat, which I think is about the size of a cereal box. You can see the dimensions there. It's based on the Argo Moon CubeSat, which has just been integrated into the Artemis mission, which will be going to the moon. There are two cameras. One is high resolution and monochrome. The other is lower resolution and color. For those of you that are Star Wars fans, the Italians named the two cameras Luke and Leia. I can only assume that they did so inspired by the movies. LiCiCube will be deployed, I think, a week or so before the DART impact into Dimorphos. It will use its little propulsion to separate itself a bit, and it will fly by Dimorphos about 3 minutes after DART hits it, and it itself will then pass by, not impact, and will send the data down to Earth. The images that LiCiCube will take have the goals of documenting the DART impact, of measuring or imaging the debris cloud that we make, so that can be analyzed for, to give us more information about what happened. And then after it passes, to turn around and take pictures of the side of Dimorphos that Didymos isn't going to see, because Didymos is only going to see one side. So get that other side of Dimorphos. So here's what we know about the system, which isn't a lot, but isn't nothing, I guess. We have been taking light curves of the system, like I said, since 2013. These are some data taken from the Keck Observatory in Hawaii in January. And hopefully you can all see Didymos, the Didymos system kind of making its way across that star field. And these are a bunch of images throughout the night. So you can see the atmospheric conditions changing a little bit. I think you see a satellite going through here at some point. Didymos was close enough to the Earth to have radar measurements made back in 2003. So we have a shape model of Didymos, the larger body. We don't have a shape model of the smaller body. And then we have a decent sense of the composition. We think that the composition of the system is very much like a particular meteorite group called the ordinary chondrites. We have a lot of those rocks. So we think that this is a pretty typical object in terms of the things that hit the Earth, which is important. We're not hitting an unusual object. We're hitting something very much like the kinds of objects we think are the dangerous ones. But there's a lot we don't know about Dimorphos. Notably, its its shape. We think it's going to be more like one of these over here on the left, maybe like KW4. We don't expect it certainly to be a sphere. And some of these stranger asteroid shapes, we also don't think it's going to be this very elongated object, but we will need to actually show up and find out for real. All of these shapes below have been at least used to make sure in tests that that the SmartNav and other algorithms will work okay. As I said, there's one instrument, Draco. Here's kind of a close-up of what that part of the spacecraft looks like with the cover open. This is Draco right here, and Draco is going to be the star of the show here as we kind of get in there to Didymos. So about a month before the impact, so this would be kind of late August of 2022, the camera will detect the Didymos system for the first time. Earlier than that, it won't have been close enough. It won't have been bright enough from the point of view of the spacecraft. Once we get about 10 days out, we are continuously, have continuous communication with the Earth. About 8 hours out, we begin our terminal phase, our last moments here, or that last phase of the mission. At 4 hours out, I think maybe I said 8 before, but at 4 hours out, SmartNav takes over. This is what the system looks like from DART, or a simulation of what the system will look like from DART at that point, 4 hours out. An hour out, you can just kind of start to see Dimorphos. The orbit is such that Dimorphos will come out from behind Didymos, so that's when it gets separated enough to be detectable. At 4 minutes out, this is what the whole system looks like. So not a whole lot of detail, certainly not a whole lot of detail on Dimorphos. And again, we're only 4 minutes out. The spacecraft is moving at 6.5 kilometers a second. I don't know my geography well enough to say, usually I'd like to say that means you could get from, Bengaluru to Mumbai in 2 minutes or something, but I don't actually know how far apart they are. So, but 6 kilometers a second is pretty fast, no matter how far you're going. At 2 minutes out, SmartNav takes its hands off the wheel, and we just coast in from there. At that point, as we say, Didymos is a couple hundred pixels across, and is slowly, we're getting close enough that that it no longer will appear in the images. And Dimorphos is only about 40 pixels out. 20 seconds before the impact, we get images of Dimorphos that are something like 50 centimeters per pixel. And we are, in order to meet our requirements, in particular this requirement about beta, we need to know where we hit. We need to know the conditions at the point where we're going to hit. We need to know if it's rocky or smooth, whether we're about to hit a giant boulder. All of those details will be necessary to interpret things correctly. And then we don't get those images until the last couple of, within the last minute. And sorry, I see questions coming in chat, but I think I'm not supposed to answer them until the end. So I will try to make sure I do that. So we will take images with Draco right up until the impact happens. So we're hoping to have a few. We're hoping that we'll have 2 or 3 or maybe even 4 images within those last 20 seconds that will be sent back to Earth. That will give us all the close-ups we need before we're done. Oops, I thought that would work. Okay, so of course all this data is going to be taken, or it's going to be analyzed by people. This is a view of most of our investigation team. This is a meeting we held earlier. I think maybe one of my hosts can find himself in this picture because I spotted him earlier. As noted, the theme of Space Week is women in space. I'm not a woman, but there are many important women on DART. Our lead engineer, who's in charge of all of the engineering aspects, Elena Adams, is here right under me. Nancy Chabot is the coordination lead. She's effectively the project scientist. Elizabeth Dotto, here to the right of my picture, is the woman who's in charge of LiCiCube for the Italian Space Agency. There are other working group leaders. Angela Stickle is in charge of the Impact Simulations Working Group. Christina Thomas is in charge of the Observers Working Group, who will be making all the measurements. Carolyn Ernst is the instrument scientist in charge of Draco. So we are. I am glad that we have good representation from all genders. You can also note it's an international group. And there are people here from probably a dozen countries in this picture, including India. And that's in part because planetary defense is an international issue. As I said at the start, when you're looking at the map, impacts can happen anywhere, and they can be problems anywhere on Earth. The United Nations has committees that are looking at this, looking at planetary defense. And Didymos, after we arrive at Dimorphos in 2022, the European Space Agency will be sending another mission called Hera to the system to rendezvous a few years later, and to do a close-up look at what DART did, get a close-up look at the crater made on Dimorphos, and make other measurements that we can't make because we're coming in so fast and going straight to impact. So next, let me see. I'll talk about kind of the status of the spacecraft. There's a short movie here, which kind of shows the last year. All of these things have occurred, but it kind of shows you what the spacecraft looks like compared to people for that scale. Some of the tests that were done here, you can see the panels open. There's the antenna, the phase antenna. Spacecraft gets put onto a table and then undergoes tests that basically try to simulate what launch is like by shaking it, making sure nothing breaks. These details you already saw. This is a Falcon. This is obviously not us. This is a different Falcon 9 rocket. As for our current status, DART was shipped from APL, where it was built in Maryland. That's there on the right, for those of you not familiar with North American geography. It started here and was driven west in a 40 to 42 hour long trip that took it to California. I don't know which of these three paths it took. But it made it fine to California. Here's a tweet from APL that shows it getting loaded on the truck, and there's the truck. It arrived in excellent shape. They've been doing tests to make sure that it came through the trip fine, and there's no problems. So everything is looking good for launch in November as planned. And then the final slide I have here is a trailer, and I think this is linked on YouTube. It is on YouTube, whether it's linked to this particular talk or not. You can find it, and this shows the. Do I have to start it? Maybe I do. This shows the life of the mission. So these are all animations. Here it's getting deployed in space. you're going to see the solar arrays getting rolled out while it's still over Earth. The covers for the ion engine and Draco are opened. Here it is leaving on the way to Didymos. The ion engine is tested. LiChaCube is deployed again just a week or so before we arrive at Dimorphos, and then LiChaCube's solar panels open up. Draco takes images. I don't know why it's in feet, but that's the way it goes for the U.S. mission, I guess. And then DART comes in for the impact. And then we have the little branding bit at the end. So that is, I believe that is my last slide. So I'm happy to take questions. I don't know if we run, if I run the questions or if, whoops, sorry. Or if Chrisphin or someone else runs the questions. So
yeah, we will take up the questions and share with you. Yeah, show me. Before going through the questions, I'll ask the participants who are within the Zoom. You have the option to unmute and ask yourself. Maybe you can try that. So that reduces stuff. Hello? Okay. Okay, so one of the question like Jugi, what was that yellow coating or film over Draco in previous slide? Maybe while showing the slide, she asked that.
Yeah, let me see if I can find the slide. Let me see if I can find the slide. Sorry. So let me share again.
Yeah.
Was it this slide?
I request Zoom participant, please, you can unmute yourself. No, no, you can unmute and ask. Feel free. I have the option. You can unmute by yourself.
Hello.
Let me see.
Yeah, go ahead.
Oh, is it this?
After that, I think previous one.
So, is it if you're talking about kind of right in here, the color?
Actually, it was golden cover type something. I had seen many times in many satellite yellow type of coating, but I don't know the name of it.
Oh, I don't know the.
No, probably she is talking about that covered up satellite covered with.
Yeah, it could be. I'm sorry. Now I'm going through this way too fast to try to find it. It could be the cover.
Yeah.
But there are also filters that are put in front to so that you know the light. So you know the wavelengths of light that are reaching the detector. So sometimes they'll put filters in. I don't know the details. I'm mostly dealing with the ground-based telescopes and not the spacecraft. But that would be my guess, is that depending on which picture, either that it's a cover or that it's a filter.
Jugi? Is it answer? Okay. And Sohan Ganguly, he asked, can you please repeat the technique used to measure the change in distance?
So we have I'm kind of do two things at once here. The change in distance from between the moon and the main body. So the the technique we're going to use is measuring the light curve of the system. So we're measuring the brightness of the asteroid system going up and down. In the simplest case, what we're doing is the light dims as the moon moves in front and then moves in back. In reality, even just there's other things going on that have to be taken out. The main body itself is rotating, and that also causes brightness variations. But we can measure now, and we can say, okay, this happens. The moon moves in front and moves in back. So things get dim twice every orbit. Once in front, once in back, and so that tells us that Dimorphos is moving around in 11.92 hours. And then afterward, we'll do the same thing, and we'll say, okay, it's moving around in every I'll make up a number, 11.78 hours. We know the circumference of the orbit. We know the time that the orbit takes. So that gives us a speed. And then also from Kepler's, if you literally mean the change in distance, Kepler's laws tell us the relationship between an orbit period and an orbit size. So by getting the period, we can get the semi-major axis. We will know how we've changed the period, so that will tell us how much we've changed the semi-major axis. Was that hopefully that was the question? If not, I'm happy to try again. But
yeah, and the next one is Jugi person. If asteroids are dangerous to our Earth, can't we do something like send an self-exploding satellite that goes near it and destroy the asteroid?
So that would, in a sense, that would be choosing to do the nuclear package. But usually when we think about this, we don't want to blow up the asteroid because we want to move it and keep it in one piece. Because we figure if we can move it and keep it in one piece, then we can just keep track of it. If you blow it up, then maybe you're going to have 20 pieces, and maybe some of them are still going to hit the Earth. And now instead of having one big thing to worry about, you've got maybe a few more things to worry about, and they're not going to be that much smaller. So usually we think about just moving a body intact out of the way.
And again, I'm repeating, Zoom participants, please, you can unmute yourself. You can directly ask the question. Feel free.
Maybe they're shy.
Yeah. And okay, another question from Brajwal Anand. For how long does DART stay in Earth orbit before getting a push into the asteroid orbit?
That's a great question. I should know the answer, and I don't. I think I think it's not long. I think it's maybe a day or less, but I'm afraid I don't know the answer to that.
Okay. And there is
someone's raised their hand.
Yeah.
Someone's raised their hand.
Yeah, please unmute yourself.
Yeah, sure. It is.
Yeah, thank you.
So what I would like to ask is that there's a plan to release another satellite called the LISA Cube prior to DART hitting the asteroid. So what happens right after the LISA Cube takes images of the impact and the impact zones? It goes around and comes back, but then what happens after that? Does it stay in orbit or crash itself or something like that?
So LISA Cube will be in a heliocentric orbit, just like Didymos and Dimorphos. It will pass by, but its orbit around the sun keeps it pretty close to the Earth as these things go for several weeks. And over that time, it's going to send the data down to Earth. The Italians have not decided what to do after that. There's not a whole lot of fuel. These things are very small, so I don't think they can. I don't think that they can go do anything else. Go to another object. I think it's very likely that they'll just take additional data on how long how their electronics work, how their communications work. They have another, like I said, another similar CubeSat going to the moon. They might just use this as a chance to take data on how their CubeSats go and how to make them last longer in space. It has solar panels, so I think the problem will be eventually it'll get too far from Earth to communicate.
Okay, well, thanks. I had just another question. Like, you are collecting data on the basis of whatever happens or the change in the orbit and all. So, what happens after this? Like, is there another mission planned to do something even different, or this is it? Is the data is only important?
So Hera, the Europeans will show up a few years later and take do follow-up observations of what we did in the Dynamo system. Every 10 years or so, the United States planetary science community goes through an exercise and says, what is important to us? What do we want to try to do in space over the next 10 years, in planetary science over the next 10 years? So that exercise is going on right now. Planetary defense is not a big part of NASA's budget. We're very happy that it's any part at all. It didn't used to be, but compared to things like sending Mars missions or anything like that, it's very small. So I think what's most likely is that the next planetary defense mission will be a space telescope to look for hazardous objects. Something that you may have picked up is that the longer the lead time we have, the longer the warning time we have, the more options we have, and you can do a deflection like DART and just move things a millimeter per second, change the speed by a millimeter per second, and if you have 50 years of warning, that's plenty. So I think that telescope will be next. After that, the group that's looking at our priorities are probably going to come up with something. Maybe it would be another DART-like mission to a different kind of asteroid, or maybe it'll be a tour to take images of near-Earth objects. I'm not sure, but certainly there's interest in continuing to send missions that are relevant to planetary defense.
Great, thank you.
Yeah, Dhanush, do you want to unmute and ask yourself? Okay, fine. Okay, I have one question, maybe off the line, or okay, fine. While sending the spacecraft or anything in the above Earth for these type of missions, like for example, this Elon Musk Starlink satellite or our DART mission or anything, is there anything like we have international policy, like because it's like Earth is our home, right? Like one planet for everybody. Like is there any thing that recognition from all the countries? Okay, this can be done, and we can send something like that. And even considering this question into the lower level, even these days all the engineering students also started like sending satellite, etc. So we are almost like just for learning purpose they are doing, but again space debris is increasing. So it's randomly people are sending CubeSat, NanoSat, this everything. So is there any policy that somebody is controlling? Okay, this can be done, this cannot be, do something like that.
Yeah. So for planetary defense, and then I'll say what I think I know about space debris. So for planetary defense, there is a UN group. They've come up with guidelines of the situations where they'd say, okay, we're going to send a mission, we're not going to send a mission. DART would fall into the category of, we needed to get whatever permissions from, obviously NASA's going to fly it, but since it's going beyond the Earth, and space beyond the Earth is pretty big, so they're not so worried about that. The Starlink satellites, things like that, That's a great question, and it is a definite thing that lots of people are thinking about. My understanding is that under the Outer Space Treaty, the country from which satellites are launched is responsible for the behavior and consequences of the satellites. So since Starlink is is launched from the United States, if a bunch of Starlink satellites hit the space station or hit the Chinese space station, God forbid, then the US would be the ones on the hook. I think that as there's been a lot of concern, as I'm sure you know, and you're probably referring to the Starlink satellites and other mega constellations affecting the night sky and affecting astronomy. And the American Astronomical Society has been trying to work to figure out the effects and try to work with the satellite providers to minimize them. But I don't know how it's going to go.
Okay.
I don't know how it's going to go.
Okay. Okay, fine. So, is there any last questions from the participants? You can unmute yourself.
Yes, I would
Shweta?
like to ask a question.
Yeah, please.
Hello, Mr. Rivkin. I'm Shweta. I have a question. You talked
Yes.
about using the mass of the spacecraft to attract asteroid away. But is it feasible, meaning the asteroid weighs little tons, right?
Well, it is theoretically feasible, and it is. If you remember the graphic, it's the sort of thing where you'd have to say, okay, we have 100 years to do this, and we have a small object. There are technical parts of it that I don't think people have thought about, like keeping a spacecraft operating for 100 years, but the theory seems to work out. This was going to be tested a little bit when during the Obama administration. There were plans to bring an asteroid or a piece of an asteroid back, to put it in orbit around the moon and send astronauts to then visit it. That is no longer the plan. But as part of that plan, they were talking about using this robotic spacecraft to pick up a boulder from an asteroid and to make itself more massive, and then use that to test this technique. The speed changes would, again, be very, very small. DART is going to change the speed of Dimorphos by something like 1 millimeter per second. We're probably talking about, 1/100th of a millimeter per second or 1,000th of a millimeter per second speed changes for the gravity tracker, at least at first. But if you have long enough, if you have enough warning time, it would work. People are also looking at other techniques besides those 4 I talked about, some of which are again, in theory look like they would work, but in practice it's hard to imagine actually doing them. But people will keep studying them.
Maybe for the smaller asteroids, but the bigger asteroids, I think it would be different. Thank you for the explanation.
Yes, absolutely, and I agree. The larger ones people are not gonna be content to sit and wait for 100 years to have this very, very slow thing move a very dangerous asteroid out of the way. But maybe that's human nature.
Okay, so if there are no questions, Aishwarya Jadhav, do you want to unmute and ask yourself? Okay, the question is why asteroids live there in orbit and come towards Earth?
Yep, that's a great question. And it was an active area of study when I was in school, when I was an undergraduate and a graduate student. There are basically it comes down to these non-gravitational forces that are very small, that are related to something called thermal inertia. So the hottest part of the day, as I'm sure you know, right? The hottest part of the day is not noon on Earth. The hottest part of the day is a little bit after noon, because it takes time for things to heat up. So that's also true on asteroids and on anything. And asteroids don't have atmospheres. So if you do the math, that means that the incoming vector of sunlight points from the sun to the object, but the outgoing vector of infrared light, of heat from the asteroid, is pointed in a slightly different direction. That leads to a very, very small force called the Yarkovsky force. And on planets, it's so small it doesn't matter. Asteroids are small enough that this very small force can actually change their orbits. It causes them to slowly move inward toward the sun. And so asteroids that are of the right size, that are in the asteroid belt, are slowly moving in toward the sun. And then there are parts of the asteroid belt that are in resonance with Jupiter. So they'll slowly move in until they reach one of these resonances with Jupiter. And then Jupiter's gravity very quickly changes their orbits to make them start crossing the orbits of Mars and the Earth and Venus, etc. So asteroids kind of have this life cycle once they get to be a certain, if they're of a certain size, where they start in the asteroid belt and then they slowly move in, and then very quickly on a geological timescale, over the course of millions of years or tens of millions of years, their orbits change. They'll either hit a planet or hit the sun. That's what they do.
Okay, and I have one question. Is there any specific reason why we have chosen Didymos as an object? Because I checked the orbit. After some years, it's passing nearby also. So I had a doubt, okay, is there any other hidden agenda or something work is there? We have chosen that object?
That's a great question. And I need to send you that paper still, I know. So the reason that Didymos was chosen, as I said in one of the early slides, kinetic impactor has been a high priority to test for mitigation for a little while. And the Europeans did a study looking at such a test in the early 2000s. And they said, okay, it's going to cost this much money because, we're looking at this one object and it's hitting, when we're going to hit it, the object is moving around the sun at 30 kilometers a second. And to measure a speed change of like a millimeter a second compared to moving around the sun at 30 kilometers a second, you need a second spacecraft to sit there and watch what's going on. And they thought that was too expensive. They didn't want to do it. So Andy Cheng, who works with us and is the other investigation team lead for DART, realized that if you went to a binary asteroid and you went to one of these eclipsing binaries, then you could do the measurements from the Earth, and you didn't need a second spacecraft, and that would make it much cheaper. So that means now that you need to find an eclipsing binary asteroid that passes close enough to Earth that it gets bright enough to make these measurements, that has a moon that's small enough that you can hit it with a spacecraft of the size we wanted to send and make that change. So Didymos is really the only choice, at least the only choice that we knew of when we started to develop the mission. And then if we didn't do it this year, there was, we could have put it off a year or two, but it wouldn't have been as easy to measure from Earth. And then if we didn't do it then, we need a whole new target. And like I said, we don't have really good targets.
Okay, then. So I think we can wind off. It has been almost more than an hour. Okay, so thank you for all the participants, and you can keep looking if there is any event on our webpage and social media pages also. And I thank Andrew Rivkin for his time with us, and hope so. Right now, I don't know how many people are aware of the DOT mission. It will be going to be in the media news by next month, November. So we should catch and Andy quickly as a first talk with us. Okay. So have a visit there. I think they are doing any live stream publicly for this mission, that mission.
I expect that the launch will be on on television. It's going to be I guess it won't be too bad for you.
Okay.
It'll be 10:30. It'll be 1:30 a.m. here, so it should be a reasonable time for you. And then yeah, the last moments, I think we're probably gonna
And this
send those images
recent
out
mission
there.
also, Lucy mission also there, man. October 16th. Something.
Oh yes,
Trojans.
yes, that's right.
Okay.
That's right. The Lucy mission is coming up soon too.
So these are all both are independent, right? Dart and Lucy. Okay.
Yep.
Okay. So there are many upcoming missions for the next decade. I mean, upcoming years. So we can keep engaged with our space activities. And it was nice talk in the World Space Week, a suitable one also. And I thank Andrew Rivkin for once again for his time. And yeah, thank you, audience. And yes, I'll just wind up this Zoom talk, and we'll be there. I will close the live stream. 1 minute.
Yep. Thank you. Thank you for having me.
Yeah.